Hi everybody, this is Bobby Smith. I'm an RF hardware engineer with Epic Solutions. Today I'm going to be talking about phase coherence in software-defined radio. We'll go through and actually define what phase coherence is, how we measure it and prove it, and I'll go through a practical example using our Sidekiq X4 software-defined radio. So we've been to quite a few of these conferences, but for those of you who aren't familiar with Epic, we are a software-defined radio company. We've been in business for about 11 years now. Our central location is now in Rolling Meadows. Recently moved out of a smaller office in Schaumburg because we're growing. We have now 47 folks, and most of us are engineers. We cover the gamut of what you would expect in an SDR company, from hardware to software, DSP. We have a few mechanical engineers and all the things needed to bring a product to bear to market here. My background here, I've been with Epic for 8 years now. We were quite a bit smaller when I started. Previous to that, I was working mainly in the DoD space. Some of the products I've worked on that you can find on our website are the X4, the Sidekiq X4, Sidekiq X2, Phase-coherent, which is a GPS card that we also sell, and a quadratic. And there's a lot of things I've worked on that are not commercially available, just for customers. We do some of that as well. So let's get right to it. So let's talk about phase coherence and what the difference is between being phase coherent and phase locked. A lot of folks tend to confuse this, and it's sort of hard to even explain in words. I'll have some GIFs to show you the difference here in a little bit. But a phase locked signal is one in which, like looking at this diagram here, we have two phase lock loops that are fed by a common reference. And so a phase locked signal is one where the two signals, when they're tuned to the same frequency, their phase relationship is not changing. Phase coherent is a subset of being phase locked. In a phase coherent signal, you can tune one signal away to a different frequency and come back, and it will maintain the same phase relationship that it had. So pictures are always better than just explaining with words. Right here is showing the behavior of two phase locked signals. As you can see, signal 2 tunes away to some other frequency, and then when it comes back to the same frequency as signal 1, its phase relationship is random. It's different. Now, it's not moving. That's why it's phase locked, but it isn't always predictable where it is. Now, contrast that with the phase coherent behavior here. This doesn't necessarily have to mean that the two signals are right on top of each other, but every time it tunes, the signal tunes away, it comes back, the phase relationship is right where it was before. And that is the definition of phase coherent in a GIF. So why do we care about this? Well, in a lot of modern systems, we're using things to determine what the phase difference is between two signals. We need to know what it is in our LO, because that ultimately decides what it's in the baseband. So think of things like antenna beamforming, adaptive arrays, and direction finding, and the 5G stuff is using all of those things. And if you have a system that is only phase locked, you have to have some way in the system to determine when you tune frequency what the phase relationship of your LOs are. And this requires you to use some type of calibration, usually like a transmit signal, or you can distribute signals the same LO to all of them, but these all come with complexity. With a phase coherent system, you really only need to calibrate it when you build it, and you can just go from there. So this is a typical phase coherent system, the way it's generally distributed. Here on the left-hand side, you can see this TX signal I was talking about, which is every time the LOs tune, there's 4 independent LOs on the left-hand side there. You have the situation where you don't know where the phase relationship between the LOs are, so you need to figure that out. This requires some sort of calibration signal to be transmitted out of the TX channel and into all 4 RX channels to kind of figure out where they're at, apply the cal factors, and now you're ready to start receiving. This greatly increases, obviously, the tune time that would be available to your system when you're going from frequency A to frequency B. Another way they do it is on the right. It can be done is when you take one LO and you distribute to all the mixers, so they're coming from the same exact source. This works, but sometimes it's not practical because some of the signal levels you need to drive these LOs are pretty high. So think if you have to drive a plus 13 dBm signal into several mixers, and now you have to distribute that 4 ways, it becomes inefficient. So we've developed a radio to sort of tackle this phase coherency problem. It's called the Sidekiq X4. There's a picture of it here. It's an FMC form factor, so any host that'll support an FMC 57.1 can hold a Sidekiq X4. It's got 4 receive and 4 transmit channels, 200 megahertz bandwidth on the receive, 16-bit A to D converters. We're going to be talking about receive today, so I'll focus on that. And all this is controlled with our Sidekiq API, which some of you may be familiar with. But this has 2 ADRV 9009s on it, and here's like an overall really high-level block diagram showing the clocking structure. And these are the RFICs from analog devices that support phase synchronization between them. So here you can see there are 2 independent LOs. This is the A chip, hence the channels A1 and A2, B1 and B2 here, and this is like the B chip over here. These are independent LOs, even though they're fed from the same reference clock. But as I'll show, you can phase synchronize these so that the phase relationship between the LOs, and then therefore can receive phase synchronous samples over all 4 channels. I'll reference these channels A1, A2, B1, B2 in the future, so this is just a visual diagram of what that actually looks like. So here's a calibration / test setup that we would normally use for what we have done here in the lab. We stimulate through a 4-way splitter all 4 channels with broadband noise. Now, every Sidekiq X4 is going to have phase differences in the RF front ends that are going to come into play here, and there are slight differences in the LOs as well, since, like I said before, the LOs are independent. The splitter plays a factor in this, but you can imagine any customer that's got a front end that they're going to stick on in front of an X4 or any platform that supports phase coherency. They're going to have to find some way to calibrate out all of those differences because they add up, and we're going to show you how to do that. The reason we use noise instead of like a CW signal, for example, is because a CW signal is periodic, and so it will correlate every 2 pi phase shift. So there's really no way to differentiate with like a CW signal, whether you're exactly on phase or you're off by 2 pi. But with noise, it's not periodic, and it stimulates the entire spectrum, and so it gives you a high degree of time resolution, allows you to calibrate. And it's easy to either have or create a noise source. This noise source could be something as simple as an amplifier with a 50 ohm terminator on the input. You're just using the amplifier's noise figure to overdrive the noise figure of the radio you're testing. And as long as the noise is higher than the noise floor of your radio, you should be able to do this. So to calibrate out the differences, there's both a scaling factor and a phase factor. Most people focus on the phase factor, which is the hardest one to do, but the phase correction factor will rotate the samples to calibrate out the phase, and since the front ends are not identical, there's also going to be some scaling involved, and we have to be mindful of that as well. So first, the phase factor. So as shown in the previous slide here, this one here, we're exciting all 4 channels with broadband noise. And then we're going to correlate the received samples. Each channel has an I and a Q set of samples. We correlate those together, and the correlation function is going to show a peak where the signals overlap perfectly. And the phase of that correlation function is going to tell you the phase difference between those signals. I won't get too deep into the woods here on correlation functions, but There's all kinds of information on Wikipedia and what that actually does, but a correlation is basically a signal processing way of comparing how alike two signals are, and there's a lot of information to be gleaned from it. So our correction factor is going to be actually the negative of the angle of that, because the angle of the correlation function at the peak is telling you what the angle difference is between the two set of samples. So we want to correct that out, so we just add a negative sign to it. So here is an example, rather contrived example of a correlation of two noise signals. They correlate very highly in the middle. This is actually a sync function. And so what we're showing here is where there's no phase shift between the two. So these two signals, R-1 and R1, are perfectly equal, and this correlates perfectly at the top. If you guys, here's the actual correlation function in discrete math. So like I said, if you want to dig further deeper into this, there's all kinds of stuff on the web. But this is with no phase shift, and I'll show the same thing with a slight phase shift of so this signal here is like 122.8 megasamples per second with a 100 megahertz bandwidth. There's no time delay. So in this set, as you can see, the sync function is shifted slightly. These two correlation, these two samples here, part of the correlation function, are no longer equal in amplitude. And this, you can see that if you were to superimpose this sync function, it has shifted slightly by 1 nanosecond. So this is basically showing the correlation function of a real function that is non-complex, but in reality we actually have complex signals, both I and Q, so the correlation function itself is also complex and has an angle to it. There's really no way to tell what the angle is on this other than maybe doing some math around the relative amplitudes of these. So here it shows 4 channels from a Sidekiq X4 and their I and Q correlation. So up here in the top left here you see the A1 to A1 correlation. This is perfect. There is no phase shift between them, right? So I is 1 and Q is 0. However, in channel A2 is all correlated back to A1. These are all correlated to the same reference channel, A1. That's just chosen somewhat arbitrarily. It can be any one. You just have to be consistent about it, because when we're just doing phase, one of the channels has to be chosen as the reference, and then you correlate in order. Here's A2, and then B1 gets correlated to A1, and then B2 gets correlated to A1. And this kind of tells you what the rotation would be to rotate the samples that are received on A2 or whichever channel, so that they would perfectly match the phase on A1. This is the actual, formula you would use to determine what that is. But your correlation function is going to spit out these numbers, and this is going to tell you what the phase is in degrees. And over here, I've populated this table here with what it is. So the actual angle of this correlation is negative 22.5 degrees, but we have to apply the -1 sign here to it in order to cancel that out. Okay, so now that we have I raw and Q raw, or the phase correlation of all of these 4 channels, same set of samples here. Now we're going to figure out what the scale is. This is a little easier. You can use that same noise signal that you've done, or that we've already measured, the same set of samples. We just need to calculate the mean of the FFT from all of the channels. This is you can't just arbitrarily choose the reference channel in this situation, because, for example, we're using 16-bit ADDs in this one. So we have to ensure that whatever scaling factor that we apply to these samples, they're not going to go over the maximum value of the ADD, because that's going to cause clipping. So you first determine which channel has the lowest magnitude, and that's our reference channel. And so then, by using this formula, we ensure that any K scaling factor we put on any of these samples is going to be less than 1. So for example, if you had a K value of like 1.1 and you were trying to apply that to a sample of 32,000, well, on a 16-bit A to D, that's going to result in like a value of 35,200, which is outside of the A to D values, and that's going to cause clipping. So here, the same set of samples are just shown in the non-logarithmic FFT here, and the relative, means of these samples are shown. In this case, B2 was the weakest channel, so B2 is our reference. And so for the K of every channel, we would just simply divide the B2 by the mean of B2 by the mean of the channel of interest, and that's what spits out these numbers right here. You can see K is less than or equal to 1, so you're not going to be causing any clipping. Here we've collected all of the cal factors into one table here. These are more or less polar coordinates. I mean, that's what they are. But in practice, we're going to, in the FPGA or in software, we're going to actually do a complex multiplication to these samples in order to rotate and scale them. So we basically need to convert these, the K and phi, to Cartesian coordinates. And so this is how the cal actually gets applied. So you get a stream of samples coming in from channel A1. You apply this complex multiplication to it. There's really no phase shift on A1 because it was the reference in terms of phase. But as you can see, these others do have a phase shift, and the scaling factor is included in that. So ostensibly, you could cancel out all of the differences from each of the channels by applying this complex multiplication. So let's see it in action here. So to get an idea of phase coherence, phase coherence is all about repeatability, right? You're supposed to, this phase is always supposed to come back to the same spot or very close to it. And the standard deviation of those phase differences is going to give you an idea of how accurate your coherency is. So we have to do this many, many times. So the process we used is we swept the Sidekiq X4 across its frequency range in intervals, and we performed this process of correlation and determining the K and the phi at every frequency, and we did this like 1,000 times. And I'll show you some of the data we got here. There's a lot of information on this graph, but it's kind of important to understand here. On the left-hand side are the mean values, and on the right-hand side are standard deviations. And the top row is the amplitude, or K factor. It's shown in dB actually here. Just most people think of RF in terms of dB. The center row here is the phase deltas. Again, this is the mean on the left and standard deviation of those on the right. And in the lower row here, I've actually taken the phase and I've taken the frequency out of it and converted that to time. And the reason I've done this is I wanted to show that the time actually is somewhat consistent here after some of the differences in channel A2 here. So we briefly toyed with the idea of applying time, but some of these differences have to do with the pre-select filter we have in there. So, we stuck with phase. But these two are really related, and as you can see, the standard deviation kind of goes up in terms of degrees as well, because ultimately it's the time. If you take the frequency out, it basically flattens it out. There's a couple issues here with the Wi-Fi interfering, and down here I think that's 750 LTE band that was interfering with our test. This does show you the mean and standard deviation. Assuming a normal distribution, you really want to see what it looks like on an individual basis. So, taking a couple of frequency points and shown what like the histogram looks out of all 1,000 trials here. So here's an example at 1900 megahertz. Keep in mind that the occurrences, the number of occurrences here is in a log scale. I did that to exaggerate any, outliers. If we had like one that was sitting way off, like 180 degrees or something, that we would want to be able to see that. As you can see, they're pretty tightly grouped. And you can definitely tell the difference between the chip B, which has the phase synchronization with regard to chip A. These use the same LO actually, and these would use the same LO. These are the channel Bs here. But everything is referenced to channel A1, so naturally channel A2 would be tighter grouped. It's using the same LO, and this is a different LO, and this will show you how well Analog Devices has done their phase synchronization. It's pretty tight. And that's 1900 megahertz. And the biggest thing is there's no outliers. So this sort of kind of proves that, yeah, you can be assured that you're going to be in this area with the standard deviation of like 0.62 degrees at 1900 megahertz every time you tune. And as we go up in frequency, as we've seen on the previous plot, the spread gets a little higher because you got to take the frequency out of it. And at the highest end, like 1.97. So these are 5900 megahertz. So let's verify the calibration, and we do that by taking those mean factors that we found. Let's go back here. These factors here converted to K and phi numbers that get, they get converted into the iCal and the QCal numbers, and the complex multiplication is applied on a frequency by frequency basis. And so that should theoretically cancel out all of these differences. So we did this again. We ran it almost 1,000 times. I think it's like 950. And this time we chose frequencies that weren't actually on the frequency cal points. So we were forced our algorithm to kind of interpolate between frequency points. And so theoretically, it should come back down to 0. So we did that repeated that same sweep. And as you can see, the amplitude differences basically nullified, and so are the phase differences. This is with the cal applied. So every time we tune to a frequency, each set of samples is complex multiplied by those cal factors to kind of null out. Again, we're feeding in noise, so we have a high degree of resolution here. And likewise, I've created the histograms for the cal verification steps. This is at an off frequency. I think the last one was 1900. We didn't want to choose that, so I choose something totally different. You can see this was like around 3500, which was the previous one. And this is the high end. You can see there's a little spread. I do want to point out there is a slight bias to the cal. So if this were a perfect cal, you'd be able to pull that back down to 0 exactly. And that's one of the things we're working on right now, is understanding why this. I think I have an idea why that is. But as you can see, you can certainly pull the phase difference in quite a bit. And so 2 degrees at 2 or 3 degrees at 5.8 gig is pretty tight. So that's one way. That's how we calibrate the Sidekiq X4 and measure and improve the phase coherence. Some of the things we're still working on in this area is like I said, we're looking at reasons why there's a slight after cal bias to this, and removing that. One of the other things that we've done is really interesting is we've actually taken multiple Sidekiq X4 and we've synchronized them together. So now you have 8 channels of phase coherent X4s at a subset of frequencies. This is still a kind of work in progress here. Some of the challenges involved in this are due to the fact that we have actually 2 different FPGAs. So they're not being driven from the same FPGA. They're being driven completely from 2 different FPGAs. But we've still been able to show that phase coherent at like integer n steps of the reference. And lastly, we're now working on a new software-defined radio based on ADI's new ADR V9002, which was announced I think in June. So we should have a new radio coming out with that. It's much smaller than the X4, but that also supports phase synchronization. That's in progress right now. So a little plug here. We're always looking to hire great people. This conference especially is good for that. A lot of smart folks involved here. So if you have any interest in doing some of this work that we're doing, which is super exciting, make sure you get in touch with us. Here's some contact info for that. And if there are any questions about this particular subject that don't get answered during the Q&A section after this, feel free to email me. You can go to epicsolutions.com and poke around in there. You can find my contact info. My email is bobby@epicsolutions.com. If anybody wants to send me a direct question related to this, I'll be happy to answer. This is a very interesting subject to me, and I'm sure that I can't cover nearly in as much detail as I would like in just 20-minute conference. So if anyone's interested, feel free to reach out directly to me. Thank you very much.